Alrighty then, corn children, children of the corn, we are going to be looking at instantaneous velocity and the first derivative. Now, before you go any further, if you have not already watched the average rate of change video, you should stop right here and go back. Alright, because I'm going to be referring to this story. Remember this? At time 0 seconds, a diver jumps up from a diving board platform that is 32 feet above the water. His height at any given time is given by this function. And we said that we could find his average velocity just by using plain slope on a secant line. A plane y sub 2 minus y sub 1 over x sub 2 minus x sub 1, I think I said that wrong, is the slope of the secant line. And the slope of the secant line, when you have position and time, will give you the average rate of change, average velocity. Well, now we want to move from average to instantaneous. And here's the gig. Instantaneous velocity, not an average rate of change, but instantaneous rate of change, is corresponding to slope of the tangent line. Slope of the tangent line, that looks confusing. If you have not already watched the videos on the derivative, the definition of the derivative, and how to find it, because that's what we're going to be using, we're going to do that right now. It's the first derivative that will give us the slope of the tangent line. And in this context, the slope of the tangent line is the instantaneous velocity. So let's do it. Yeah? Awesome. So first thing we're going to do, since we don't know all the shortcuts, we're going to find the derivative using the definition. H prime of t. Now I'm going to go quickly through this. And you're also going to notice that I'm going to use, instead of delta x, I'm going to be using the variable t. So this is delta t approaches 0. Instead of f of x plus delta x, it is h of t plus delta t. Now if that's going to cause some of you to throw up, you can switch all these out and make this f of x plus delta x minus f of x all over delta x. But I've got h's and t's, so that's what I'm working with here. All right, so if you need to pause this in order to slow it down, by all means, go ahead. H of t plus delta t. In our function, everywhere I see a t, I am removing it. Do you see that? T's are removed, there's the plus 32. In the place of both of these t's, not just one of them, but both of them, I put t plus delta t. All right? Now that takes me through that parenthesis. That's h of t plus delta t. Now I need to do minus the original function. Now once again, you can either do minus and parentheses around all of this, or you can distribute this negative to the function. Now, I'm going to do that because I'm a genius. So, minus the original function becomes plus, changing the sign, 16t squared, minus 16t, minus 32, distributing the negative all over delta t. If we filled in 0 for delta t right now, we would get 0 over 0. Well, that means we need to factor, cancel, and plug back in. So, in order to make it factor, we are going to multiply this all out, distribute the negative 16, distribute here, and combine all of our like terms. I'm moving quickly here. Recall that this squared is t squared plus 2t delta t plus delta t squared. If you need to do that slower, go ahead. I am also going to distribute the negative 16 to all of those terms. So this part, this first term up to the, well, this first part up to this plus sign becomes negative 16t squared, negative 32t delta t minus 16 delta t squared. That takes me up to here. At the plus sign, I distribute the 16. Distribute. And then I just bring all the rest down. Now, you can cancel earlier than this. I like to do it all at once because it's very dramatic. Almost wrote an X. All right, look carefully. Do you see what I see? Negative 16t squared, positive 16t squared. Silly terms, they cancel out. Hey, look. Positive 16t, negative 16t. Cancel. 32, negative 32. And by the way, if these aren't really canceling, if you're fudging it, you screwed up. These need to cancel. All right, look at it. Every remaining term in the numerator has a delta t. What was our goal? When we get 0 over 0, we want to factor, cancel, plug back in. I can factor out a delta t. And because I can, I will. Limit delta t approaches 0. You still writing it? You should be. Delta t comes out. It is it may not be the greatest common factor. It isn't. It's a common factor. Negative 32t. Negative 16 delta t. Plus 16. All over delta t. There's the factor. Here's the cancel. Whoosh, whoosh. Here comes the plug back in. Now look, it's right here. It is not t that's going to 0, it's delta t that goes to 0. We have a delta t right here. That term will go to 0, leaving behind negative 32t plus 16. Here's what I'm telling you. The derivative of h is negative 32t plus 16. But here's what I'm also telling you. This function of t is the instantaneous velocity function. What? Here's what I'm saying. You fill in any time and out will come the velocity at that time. Are you kidding? No. If you plug a 1 into this, you will get negative 16. Here's what that means. At the time of 1, the slope here of the tangent line is negative 16. At the time of 1, the instantaneous velocity is negative 16 feet per second. No way. Here's what else it means. You plug in a different time, you'll get the velocity at that time. This gives us the velocity to this curve at any time you plug in. Yes, I know. It's crazy like that. That is awesome, isn't it? Hope you enjoyed that.